In this video, we're going to focus on Bernoulli's equation to solve physics problems. So let's start with this one. Water flows through a horizontal pipe with a cross-sectional area of 4 square meters at a speed of 5 meters per second with a pressure of 300,000 pascals at point A. At point B, the cross-sectional area is 2 square meters. What is the speed of water at point B? So let's draw a picture. So we have a horizontal pipe and the cross-sectional area is being reduced. So this is going to be point A and this is going to be point B. So at point A, the speed of water flowing is 5 meters per second. We need to calculate the speed at point B. The area at point A is 4 square meters, and the area at point B is 2 square meters. So here's a question for you. If the cross-sectional area decreases, what's going to happen to the speed of the fluid? Anytime you decrease the cross-sectional area, the speed of the fluid will increase. And the equation that we could use to get the answer is the continuity equation for an incompressible fluid. A1V1 is equal to A2V2. So A1 is 4, V1 is 5, A2 is 2, and we're looking for V2. So V2 is going to be 4 times 5, which is 20, divided by 2, which is 10. So at point B, the speed of water is 10 meters per second. So if you reduce the area by a factor of 2, the speed will increase by a factor of 2. So now let's move on to part B. Calculate the pressure at point B. So P1 is 300,000 pascals. We need to calculate the pressure at point B. So will the pressure be higher or lower? So one aspect of Bernoulli's principle is that the pressure is high when the speed is low, and the pressure is low when the speed is high. So because the fluid is moving faster at point B, the pressure has to be lower. In fact, as the fluid moves from A to B, it's accelerating. So therefore, there has to be a net force that will accelerate the fluid from A to B. And pressure is associated with force. Pressure is force over area. So therefore, in order to accelerate the fluid towards the right, the force at point A has to be larger than the force at point B. So therefore, in order to get that net force in the positive x direction, point A has to be at high pressure and point B has to be at low pressure. So now let's calculate P2. So we should get an answer that's less than 300,000 pascals. So let's use Bernoulli's equation to get the answer. So here's Bernoulli's equation. P1, the pressure, plus rho g H1, where this is the density of the fluid, plus 1/2 rho V1 squared. That's equal to P2 plus rho g H2 plus 1/2 rho V2 squared. Now the height of the pipe does not change. So therefore, these terms are insignificant. P1 is 300,000 pascals. The density of water is 1,000. On the left side, water flows at a speed of 5 meters per second. We're looking for P2. And the speed on the right is 10. So let's erase a few things. 1/2 of 1,000 times 5 squared is 12,500. And if we add 300,000 to that, we have 312,500 on the left side. On the right side, that's P2 plus 1/2 of 1,000 times 10 squared, which is 50,000. So P2 is going to be 312,500 minus 50,000. So the pressure at point B is 262,500 pascals. So notice that it's less than the pressure on the left side, which is 300,000. So as we can see, as the speed increases from 5 to 10, the pressure decreases from 300,000 to 262,500. So what you want to take from this is that as the speed increases, the pressure in the fluid decreases. They're inversely related. Now let's talk about how we could derive the equation, the portion of Bernoulli's equation that we use to get the answer. So we know point A has a pressure P1, point B has a pressure P2. And so because the fluid is accelerating towards the right, we know that F1 has to be greater than F2. And as the fluid accelerates from a low speed to a high speed, the pressure decreases. And so the work that's done by the net pressure, or the pressure difference between points A and B, is equal to the change in kinetic energy. The kinetic energy of the fluid is increasing because it's moving faster. So we could set W equal to delta KE. Now work, we know it's force times displacement. And the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. Now keep this in mind, this is the net force. Now, if we multiply the top and the bottom by area, on the left side, what we could have is the net force divided by area times displacement. Area times displacement, or area times height, that's equal to volume. And the final kinetic energy is 1/2 mv final squared. And the initial kinetic energy is 1/2 mv initial squared. Now force over area is pressure. So this is going to be the net pressure, which is basically the change in pressure, the difference between points A and B. So that's force over area. So we have the change in pressure times volume is equal to everything on the right side. Now what we need to do is divide every term by the volume. On the left side, we could cancel the volume, and we could replace delta P with P1 minus P2. Mass divided by volume is density. So this is going to be 1/2 rho, which is m over v, times v final squared. So that's going to be, let's say, v2 squared minus 1/2 m v1 squared. I mean, not m, but rho v1 squared, because that's mass over volume. So I'm going to take this pressure and move it to this side, so it's going to be positive, and take this value, move it to that side, so it's going to be positive as well. So this is going to be P1 plus 1/2 rho v1 squared equals P2 plus 1/2 rho v2 squared. So this is the portion of Bernoulli's equation that we use to calculate the new pressure at a different speed. So it comes from the work energy principle. Now let's work on this problem. I wrote number 1, but this is supposed to be number 2. So water is flowing through this circular pipe with a constant radius of 10 centimeters. We're given the speed and pressure at point A. What is the speed of the fluid at point B? And also, what is the pressure at point B? And point B is 10 meters higher than point A. So go ahead and feel free to use Bernoulli's equation to answer parts A and B. You can pause the video if you want to. Now the pressure at point A is 250,000 pascals. And the radius, it's constant. The radius doesn't change. So the radius at point A and point B is 10 centimeters. So first, what is the speed of the fluid at point B? We know that if the area decreases, the speed will increase. And if the area increases, the speed will decrease. However, the radius of the pipe doesn't change. So the area is constant, which means that the speed has to be constant based on this equation. So if A1 is equal to A2, V1 is equal to V2. So the speed is not changing. So the speed at point B is 4 meters per second. The only thing that's changing is the height. Now we know the relationship between speed and pressure. As we saw in the last example, if the speed increases, the pressure is going to decrease. So in this problem, the pressure is not going to change due to speed. The speed is constant. So if the pressure changes, it has to be due to the height. So let's say A is at ground level. That means B is at a height of 10. If we increase the height, what's going to happen to the pressure? Now, in the first scenario, in the last problem, the pressure decreased because energy was needed to speed up the fluid from a low speed to a high speed. In this example, the pressure has to decrease in order to increase the gravitational potential energy of the fluid. In order to lift the fluid from point A to point B to work against gravity, the pressure has to decrease. So what you need to know is that at a low elevation, the pressure is high. So the pressure is high at the bottom and it's low at the top. So whenever you increase the height, the pressure will decrease. So make sure you understand that. So now let's calculate P2 using Bernoulli's equation. So it's P1 plus rho GH1 plus 1/2 rho V1 squared. That's equal to P2 plus rho GH2 plus 1/2 rho V2 squared. So we have P1. That's 250,000 pascals. In this example, the speed does not change. So therefore, this quantity will not change. We could cancel it. The height does change. Now, since we're assuming that A is the ground level, the height at A is 0. So we could say H1 is 0, and the height at point B is 10 meters above ground level. So H2 is 10. So because H1 is 0, we don't need to worry about that quantity. Now we're looking for P2, and this should be gone. So this quantity is important. So rho, the density of water, is 1,000, G is 9.8, and H2 is 10. So if we multiply 1,000 times 9.8 times 10, that's 98,000. So P2 is going to be 250,000 divided by 98,000. So that's 152,000 pascals. So as we can see, the pressure is lower at a higher elevation. And perhaps you've seen this if you live in a 2-story house. Now, depending on the pressure in the tanks, you might notice that the pressure on the first floor, let's say in a faucet, the water pressure might be stronger on the first floor, but on the second floor, you might notice that it might be a little bit weaker. And the reason being is at a higher elevation. So as you go up, the pressure is going to be lower. And so the water, like, you can tell that there's less pressure in the water at the top than at the bottom. Now what we're going to do at this point is derive the portion of Bernoulli's equation that we used to get this answer. So it's going to be everything except those two terms. So we're going to show that this quantity is equal to that quantity. So in this example, the pressure difference between points A and B is needed to lift up the fluid by a height h. Or let's say this is ground level, this would be h1, and this would be h2. So the difference is h. So in this case, the pressure difference has to go against gravity. It has to increase the potential energy of the fluid. So we're going to set work equal to the change in gravitational potential energy. Now, as we saw in the last example, we said that work is force times displacement. And this was based on the difference in the two forces. And then we multiplied the top and the bottom by the area. So we have F1 minus F2 over A, and that's equal to D times A. So area times displacement, or area times height, was volume. And so we have F1 over A minus F2 over A times volume. Force divided by area is pressure, so it's P1 minus P2 times volume. So the work due to pressure can be described as the change in pressure times volume, or sometimes it could be pressure times the change in volume, depending on what's constant and what's changing. So I'm going to skip this entire step and jump to W equals delta PV, just to save time. So the work done by pressure is going to be the change in pressure times volume. And the change in potential energy is going to be the final potential energy minus the initial potential energy. So mgh2 represents the final potential energy. mgh1 represents the initial potential energy. Next, we need to divide every term by the volume. So the change in pressure is P1 minus P2. And as we saw before, mass over volume is density. So we're going to have rho gh2 minus rho gh1. So let's take this term, move it to that side, and this term, move it to this side. So on the left, we're going to have positive P1 plus rho gh1. On the right, P2 plus rho gh2. So that's how we can derive this portion of Bernoulli's equation. Number 3, calculate the pressure and speed of water at points B and C shown below. So first, let's talk about the speeds. What is the speed at point B? Now, if we look at the cross-sectional area, it doesn't change between A and B. So therefore, the speed at points A and B should be the same. So at point B, the speed has to be 10 meters per second. Now, going from B to C, notice that the area doubles. And as we said before, if you increase the cross-sectional area, the velocity has to decrease. And we could use this formula to get the velocity. A1 v1 is equal to A2 v2. So, or in this case, we're going to use A2 v2 is equal to A3 v3. So A2 is 3 and V2 is 10. A3 is 6, and we got to calculate V3. So it's going to be 3 times 10, which is 30, divided by 6, so that's 5. So the speed at point C is 5 meters per second. So if you double the cross-sectional area, the speed will be reduced by a factor of 2. So it went from 10 to 5. Now what about the pressure? So at point B, is the pressure higher or lower than point A? In the last video we saw that, or in the last problem rather, as we increase the height, the pressure decreases. The pressure is low at a high elevation, and the pressure is high at a low elevation. Well, point B is lower in elevation than point A, so point B should exist at a higher pressure. So if you decrease the elevation or the height, the pressure has to increase. Now, which one is higher? Is the pressure higher at point B or point C? As the velocity increases, the pressure decreases, as we saw in problem 1. Whenever the speed increases, the pressure has to be reduced. So the pressure is high when the speed is low, and the pressure is low when the speed is high. So if we decrease the speed, the pressure should increase. So therefore, the pressure at point C has to be greater at point B, and the pressure at point B is greater than the pressure at point A. Now let's use Bernoulli's equation to calculate the pressure at point B. So we're going to go from point A to point B. So P1 plus rho GH1 plus 1/2 rho V1 squared, that's equal to P2 plus rho GH2 plus 1/2 rho V2 squared. So at point A, which is the left side of the equation, the pressure is 300,000 pascals. Now let's define point B and C to be the ground level. So the height at point B and C, we're going to say is 0. So A is at an elevation of 20. So H1 is 20. H2 and H3 is 0. They're at ground level. So this is going to be 1,000 times G, which is 9.8, and H1 is 20 meters above the reference level. Now, between points A and B, the speed does not change, so we don't need this term. And H2 is 0, just as H3 is 0, because they're at the reference level, so we don't need this term either. So now this should give us P2. So it's 300,000 plus 1,000 times 9.8 times 20. So the pressure at point B, let's see if I can fit it in somewhere. Which I'm going to call P2. That's 496,000 pascals. So as we can see, the pressure at point B is indeed higher than the pressure at point A. So the pressure is always going to be higher at a lower elevation than at a higher elevation, with everything else being equal. Now let's focus on point C. Let's go from point A to point C. So let's use Bernoulli's equation again. Now this time we need to use the entire equation. So all of the stuff on the left side is going to be associated with point A, and all of the stuff on the right side is associated with point C. So let's make this P3 instead of P2, and H3 and V3. So P1 is 300,000 pascals, and the density of water is still 1,000, G is 9.8, and at point A, it's 20 meters above the reference level. And then it's going to be 1/2 times the density times the speed at point A, which is 10 meters per second. Now we're looking for P3, the pressure at point C. And then we have rho G H3, so that's 1,000 times 9.8. Well, actually, that's going to be 0. H3 is 0, so we don't need that term. So I guess we didn't need all 6 terms of Bernoulli's equation, just 5. We do need this term though because the speed changes at point C. So it's 1/2 times the density times the new speed, which is 5 meters per second. So this is going to be 300,000, and then 1,000 times 9.8 times 20, that's 196,000, plus 0.5 times 1,000 times 10 squared, which is 50,000, and that's equal to P3 plus 0.5 times 1,000 times 5 squared, which is 12,500. So we need to add 300,000 plus 196,000 plus 50,000 and take that result and subtract it by 12,500. So the pressure at point C is 533,500 pascals. So notice that the pressure at point C is indeed higher than the pressure at point B. So if you want to increase the pressure of a fluid, all you got to do is decrease the elevation. As the fluid falls down, the pressure increases. And the second way to increase the pressure is to increase the cross-sectional area. As you increase the cross-sectional area, the speed slows down and the pressure of the fluid increases. Now let's talk about how to derive the entire equation for Bernoulli's principle. So let's say this is point A and point B, and the fluid enters at a speed of V1 at point A and leaves at a speed of V2 at point B. And at point A, it's at a height h1 above the ground. Point B is at a height h2. And point A has a pressure P1, point B has a pressure P2. Now let's say that V2 is different than V1. In fact, let's say that V2 is greater than V1. So it's going to take energy to increase the speed of the fluid. In order to increase the kinetic energy of the fluid, to increase the speed, the pressure has to decrease. So the kinetic energy doesn't increase for no reason. It has to come from somewhere. Now, to increase the gravitational potential energy of the fluid, the pressure must also decrease. That energy has to come from somewhere. So at a low elevation and at a low speed, here it's moving slow, and here it's moving faster, or relatively fast compared to this speed, the pressure at point A has to be higher, and the pressure at point B has to be lower. So anytime you need to increase the speed, if you're going from a low speed to a high speed, the pressure has to decrease. And to increase the elevation, the pressure of the water has to decrease as well. So make sure you understand that concept. Anytime you increase the elevation, the pressure goes down. And if you increase the speed, the pressure has to go down as well. So this time, the pressure has to do work to change not only the kinetic energy, but also the potential energy. So it has to change the mechanical energy of the system. So I'm going to set W equal to the change in the mechanical energy of the system. And we know that W is going to be the change in pressure times the volume based on our other examples. And mechanical energy is the sum of kinetic and potential energy. So this is going to be the change in the kinetic energy and the potential energy of the system. Now the change in pressure is P1 minus P2. And the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. The change in gravitational potential energy is the final potential energy minus the initial gravitational potential energy. Now let's replace the final kinetic energy with 1/2 mv final squared, or mv2 squared. And the initial is going to be 1/2 mv1 squared. the final gravitational potential energy is going to be mgh2, and the initial is going to be mgh1. So just like we did before, we're going to divide every term by the volume. So on the right, v will cancel, so we're going to have P1 minus P2. On the left, everywhere we see mass over volume, we could replace that with density. So this is going to be 1/2 rho v2 squared minus 1/2 rho v1 squared plus rho gh2 minus rho gh1. So everything with a 1, let's move it to the left side. So these two are negative on the right side, but they're going to be positive on the left side. And everything with a 2, move it to the right side, which is just this one. It's negative on the left, but it's going to be positive on the right. And so this gives us Bernoulli's equation, P1 plus 1/2 rho v1 squared plus pgh1, and that's equal to P2 plus rho gh2 plus 1/2 rho v2 squared. And so now you know how to derive this using conservation of energy.